Any questions about anything? There's something in chat. That's fine. So, yeah, so, okay, so we have barely started our study of actual StatMech, and today that's what we are going to do. So last time we had talked about the concept of phase space, where the idea being that you have coordinates that correspond to position, R, and momentum, P, okay? And this R itself is R1, R2, R3n. So it's not just one line, it's a very high dimensional space with 3n coordinates. And same for P, it's P1, P2, P3, P3, and lots of things. And in this space, you could start a system at a given P, comma, R value, which means, and this, what do you mean by system? It's something macroscopic. So macroscopic system can be characterized by its P, R values, right? If you do that, then this is a microscopic description of the actual macroscopic system. You have a physical system, it could be a battery material, it could be a protein, whatever you have. And if you use all these 6n numbers, then you have a microscopic description of this macroscopic system. These 6n number together constitute a microstate. So MICRO, microstate. So if you have specified these 6n numbers, you have specified the actual microscopic state of the system. And the idea is that if you have prepared the system, and if you know the system is at one particular value of P, R, then you could solve Newton's law of motion and follow the system as it goes in time everywhere. It might come very, very close, but it's not going to cross it. It's not going to cross any of its line, and it will make a trajectory that goes in phase space. Okay, so what do we do with such a trajectory? Now let's say we want to connect it back to macroscopic things.
Excuse me?
Go ahead.
Can I ask a quick question? So in terms of definition for the microstate, are you talking about the say P1 Q1 or P1 arrow Q1 arrow? Say, are you talking about the vector or just only one component of the vector?
I have specified it right here, the 6n numbers.
Okay, so it's defined as the component of the vector, right?
Yeah, all 6n numbers.
Okay, gotcha. Thanks.
Okay. Lots of numbers, lots and lots of information. Yeah, if something is not clear, just ask me. So it's all 6 numbers that are microstate. So how do you go back from this microstate to talk about something that can be measured in an experiment? Let's say you're interested in some observable O. O could be the free energy of the system, O could be the volume of the system, something, some thermodynamic observable O. You could go and calculate it over this trajectory. Let's say the trajectory started at time 1 over here, time 2 over here, time 3 over here, time 4 over here, so on and so forth. And let's say this is time m. So you could go and calculate this quantity by averaging over these m time observations. At each of them, you go and measure OI, the value at that time, and I goes from 1 to m. This average denoted by ensemble, denoted by bracket notation or denoted by bar notation, either both of them, is called a time average. Why would you care about such a time average? You would care about such a time average is because this is what you do in experiments. You prepare a system and you observe it many, many times and you calculate the average of that system. You don't, when you are doing this actual average, you don't care about where are the different atoms in the system. All you're doing is to observe the value of the observable of the quantity O for m amounts of time, and it will change observation to observation, but you can measure some average quantity, right? This is what you do in an actual experiment. So time average is accessible in physical or physical experiments when you actually perform experiments, but theoretically it's very hard to do. In theory or in computer simulations, it's extremely hard to do. Why is it very hard to do? Because there you have to take into account how will the system go from 1 to 2. You have to calculate what is this point 2 that the system is going to take over here. So in theory, in order to go from point 1 to point 2, you have to solve Newton's law of motion for all these 6 n numbers, and that's going to be extremely slow. So time average is accessible in physical experiments, but hard in theory or simulations. So if you want to connect the macroscopic picture to a microscopic picture, we are stuck because solving this many equations of motion is going to be very hard. And that brings us to the concept of ergodicity. And this ergodicity is the first key assumption in StatMech. We are not going to prove this, we are just going to assume it. And as a matter of fact, it's not proven yet, it's a hypothesis. It's also called as the ergodic hypothesis. So what does the ergodic hypothesis say? The ergodic hypothesis says that time average is equal to ensemble average. Now, what do I mean by that? What I mean, and I don't really need to write a hyphen over here, it's the same thing. Time average is equal to ensemble average. What do I mean by ensemble average? What I mean by ensemble average is I could take this system and instead of following one trajectory for a very long time, what I'm going to do is to think about many short trajectories. I will start one trajectory from here, 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 one from here, so on and so forth. And instead of calculating an average over a very long time, I will just calculate the average of O from this trajectory, 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 and average all of them together. That's the idea. Okay? This average is, so when ensemble average is when you create many copies of the system. Instead of looking at one system for a very long amount of time, you create many copies of the system and observe them essentially for t tends to 0 for right then. You just create the copy. You don't have to solve any dynamics. You can get this information statically. So that's the notion of an ensemble. An ensemble is a set of copies of the system. Now we have to be a bit careful here. How do we make this rigorous? How does this proceed? So in order to make it rigorous, let's do it this way. So let's draw our phase space again. And anytime I write RP, I actually mean a vector because it's a 6n dimensional space, right? So I have a trajectory that went from here to here to here. And now what I'm going to do is to think about this trajectory. I will discretize this space. How fine should I discretize it? Well, we have our uncertainty principle that helps me with that, right? So I've discretized it into different microstates. Each one of these is one possible microstate, right? When you have a certain value of p comma r, even if you don't like quantum mechanics, you can still discretize it, right? It's just a question of observation. How fine are you going to observe it? So you have one microstate. This one over here is another microstate, and you have discretized the system like this. And then what we say is that our observed O, which we had as 1 over m, I is equal to 1 to m, observable I, this was our time average, right? This thing can be written, and this is the transformation I'm going to do next is actually very simple, but also very beautiful, and it will show up again and again in StatMech. So pay attention to it. Here, what was I? This was time index, right? time is equal to 1, time is equal to 2. You could even have called it t is equal to 1 if that helps you simplify the notation, but it's an index for time. Instead of index for time, let's use a microstate index. And typically in statistical mechanics, microstates are denoted by the Greek letter nu, is the Greek letter nu. Okay, so instead of observing it many times, what we do is to go and think about any such microstate. So this is one particular value of nu right over here. This is another value of nu. This is another value of nu. You go and go to that microstate, calculate the value of that observable in that microstate. So notice now, instead of OI, I have denoted it by O nu. Is that the same? Have I done everything or am I missing something? I have to take into account the probability that the system will actually be found in that microstate, right? So this is not normalized clearly. So I have to do something else. I have to, let me write it. I'm not erasing anything, I'm just fine. So I have O nu multiplied by the probability that the system actually visits that microstate. So that's the subtle thing here. When you made these copies of system, how do you know that you should have the same number of copies everywhere? How do you know that maybe the system spends more time in this part of the landscape and less time in this part, the right side of the landscape, right? You need to know that. So there is going to be a probability here, which we are going to call P nu, which is the probability of finding the system in microstate nu. So you might say at this point, well, that doesn't help me at all. In order to calculate this probability of finding the system in microstate nu, maybe I have to run this simulation long enough and then go and count. Okay, maybe one time over here, one time over here, one time over here, one time over here, 0 over here, 0 over here, 0 over here. So do I really need to do everything all over again? No, and that's the beauty. So we have just stated our ergodic hypothesis, which says that time average 1 by m I is equal to 1 to m OI is equal to ensemble average, where we completely, so here we have indexed over time. In ensemble average, we have completely removed the concept of time. We are talking about microstate nu. And we say the observable in that microstate multiplied by the probability of finding that microstate. So this is the ergodic hypothesis. It can be proved for certain types of system. If you take Chris Jarzynski's advanced StatMech class, which might be taught in a couple of years, I think he proves it for certain type of dynamics. You can see, you can actually prove this is going to be true. For general dynamics, I think it is just a hypothesis, but this is at the heart of statistical mechanics. If this hypothesis was not true, statistical mechanics would not help. The reason why it would not help, because rest of this semester, all we are going to do is to calculate P nu. We are going to spend a lot of time calculating P nu for different setups. For example, if I tell you, let me give you an example for this one. Let's to get you some intuition into P nu. So in order to get some intuition into P nu, let's consider a simple system, just a 1D system with momentum P1 and position X1, okay? Now let's say this system is inside a box where I have put in a hard partition at X is equal to 0, okay? And my particle, which is bouncing around, and this is supposed to be a 1D box, I have extended it in one direction just to give you a sense. So this is X less than 0, and this is X more than 0. And this system is blocked. It can move in this way, but it cannot cross the boundary. So in this case, you can directly say that P nu for a microstate will be 0 if the X in that microstate is less than 0, right? You can directly write this down. What will it be for X more than 0, that's hard. We will get to that in a moment. But you can directly say that T nu will be 0 for X less than 0. So just an example. So, but more generally, StatMech is all about calculating P nu or microscopic or microstate probability distribution. And there comes a keyword, which is given or conditional on. And that's why I said Bayes' theorem is a nice theorem if you're going to like StatMech. Given on what we know about the system macroscopically. So we might know a bunch of things about the system macroscopically. What could we know? For example, I just gave you an example here. We know that the system should not go in X less than 0, or more abstract, these macroscopic things might be the number of particles in the system, volume of the system. Maybe you know something about the temperature of the system. Maybe you know the total energy of the system. Maybe you know the chemical potential of the system. You cannot know everything. Typically, you can know 3 of them at the same time. Otherwise, it becomes over-parameterized. So statistical mechanics is all about figuring out P nu. And every ensemble is a different set of macroscopic constraints. And we will go around calculating our P nus for these different ensembles. The reason why we would like to do that, because once we know our P nu, we can do theory to calculate bulk properties of a system without having to do experiment and measure the time average, or without having to do simulation and follow the system as a function of time. Both are very useful. Simulations are useful, experiments are useful, but they have their limitation. Theory, on the other hand, if you can figure out what's a P nu, you can do it quite easily. So what is the first P nu that we are, and did I miss anything here? No.
So I had a quick question. So in the previous slide or the page, what's the term that's multiplied with P nu? Is it data nu or is that sigma?
O nu.
So sorry?
O nu.
Okay.
Are you talking about this one?
Yeah, that one, yeah.
This is the value of the observable when the system is in a particular microstate.
Right, okay. Yeah.
So instead of saying that this observable had a certain value at time 0, at time 1, at time 2, at time 3, you are thinking about the value of the observable in space, in phase space. So that's
right, okay.
It's abstract. And we will be switching this perspective again and again. It's almost as if you have transformed the space. You have gone from a time representation to a position representation. Okay.
Okay.
So our first ensemble, which is really the heart of statistical mechanics, everything else is this ensemble plus a bit of Taylor series. That's it. Our first ensemble has a very funky name, even though it's a really, really simple ensemble. It's called a microcanonical ensemble. What do we mean by microcanonical ensemble? It is also called as a NVE ensemble. So these are the 3 things specified. So this is an isolated system with fixed total energy E, volume V, and number of particles N. These are our 3 macroscopic constraints that we have specified on the system. It's isolated, so we cannot put a thermometer inside it and go and measure its temperature. We cannot do that. We cannot couple it to a thermal bath in order to measure its temperature. It's isolated. We cannot couple it to a mass bath. We cannot couple it to a reservoir of particles and see what is the chemical potential and things like that. No, it's isolated. It's some fixed value of N, E, and V. Nothing can change. In this case, what is going to be P nu? What can we say about a system? this brings us to the second assumption in statistical mechanics. So we just saw first assumption, which was ergodicity. It is the first key assumption in statistical mechanics that ergodic hypothesis holds true. The second key assumption, which sounds abstract, but in a moment, hopefully it will become quite clear to you, is that if you can't do anything to a system, if there is no way you can go and check what's happening inside the system, you cannot put a thermometer, you cannot couple it to anything else, then all microstates must be equally probable. It sounds funky, but it's really simple, right? You cannot draw any conclusions about what's going on inside the system. You have no way of doing it. The energy is fixed, you cannot measure its temperature. You can't do anything. So in other words, this is the, and this sounds obvious, but it's actually an assumption. If you really try to think about it, it's kind of hard to prove rigorously, but thankfully it's very obvious. So the second assumption in StatMech has a funky name. The name is, what's the name? Law or equal, should I call it a law? What do I call it on my class website? Let me see one more. I don't want to use a wrong term for it. I will call it principle. It's the principle of equal a priori probabilities or possibilities. So if a system is isolated, then all microstates must be equally likely. You can't say anything. You have no way of judging whether the one microstate is preferred over another microstate, as long as that microstate has the right energy, volume, and number that you are enforcing. As long as, since it cannot exchange energy with the reservoir, with outside world, so total energy is constant. So what we are saying here is, if we go in our phase space and look at different boxes in phase space, these are our different boxes characterized by P1x1, P2x2, Pnxn, Pkxk, so on and so forth. We will consider all those boxes which have energy equal to E. So in this case, the energy of this box E1 is equal to E. This case, box number K, we find that energy Ek is not equal to E. Okay? So what this equal a priori principle tells us is that P nu is equal to constant if E nu is equal to E, N nu is equal to N, V nu is equal to V, and 0 if any of them is not true. So that's our first P nu for a macroeconomical ensemble. It's really the simplest thing you can think of. All it's telling you is that if you don't know anything about a system, if you have no way of judging a system, you should not judge it. Everything has to be equally likely. Every other ensemble will be derived from this. So in other words, we can go one step further. We can define now a symbol omega, NVE, as a function of NVE, because these are the three things that are fixed for an isolated system. So this thing becomes a bit confusing sometimes, that if we are saying an isolated system, how are we fixing NVE? Well, that's the property of an isolated system, that total energy, total number, total volume has to be constant. If it was in mechanical equilibrium and not isolated, then the volume won't be constant, the pressure would be constant, right? If it was in mass equilibrium, then N won't be constant, mu would be constant, the chemical potential. If it was in thermal equilibrium, then E won't be constant, temperature would be constant, so on and so forth. So if you have no ways of enforcing equilibrium on the system, then NVE are the things that are constant. So we define this symbol omega NVE, and see something in chat. Okay. And every time I see now a partition function, I think of Neha, because Neha said she likes partition functions the most in the first class. So now it's your fate now, Neha, for the rest of the semester. So omega NVE is our first example of a partition function. It's called many books do not use this term, microcanonical, but this is really what it is. It is the microcanonical partition function, which is the number of microstates with number n, volume V, and energy between E and E minus delta E. Why did we do that this way? Why didn't we say number n plus delta n? Because it's easy to say the number of particles you have, right? 1, 2, 3, 4, 5, 6, 7, 8. It's easy to measure the volume you have. You can enforce it. Energy is a bit funky. It fluctuates. So you can never specify energy up to 0 precision. You will have, think about measuring temperature. The lowest temperature that has been recorded, I don't know, it's maybe 10 to the power minus 30 Kelvin or something like that, but it's a finite number. So energy will always have a small difference. So you have to specify here the number of microstates between energy E and some energy E minus delta E. You cannot just say number of microstates with energy E, because that will become very ill-defined. It, however, turns out, and this is quite beautiful, and we'll be proving it in the next class, that the precise choice of delta E is immaterial. This is really, really nice. And this boils down to the fact that as you increase the dimensionality of space and you look at spheres in higher dimensional space, most of the volume of a sphere lies in its shell, in its surface. So you can imagine a 2D sphere, which is a circle, and you know how much is the circumference, you know how much is the area. Now you go to a 3D sphere, you know how much is the surface area, you know how much is the volume. You can do it for higher dimensional spheres. As you go to higher dimensional spheres, you will find that most of the volume is actually not inside the sphere, it's right on the surface. And we will use this fact next time to show that this precise choice of delta E just doesn't matter for a microcanonical ensemble. If it did, then we would have been a bit more trouble. We will do that next time. For now, I just want you to take my word of it that, so we will be doing it on Feb 9, because Feb 4, there is no class. Okay, so we will be showing on Feb 9 that this choice of delta E does not matter. For now, just take it this way. So given this, we can now write down our P nu more exactly. We can say that P nu is equal to 1 over omega of n comma v comma e for all nu with energy E in this interval, E minus delta E to E, and 0 otherwise. How do I write it? Why did I write it as 1 over omega NVE? So how did I go from this fact that, okay, P nu should be constant, and this fact that NVE is the number of microstates? How did I connect these two to write down this one? Any ideas? What property of a probability distribution did I use to do this?
Like the PV times the omega is equal to 1.
Is that true or something similar? You're close. I used that summation over all nu, P nu equal to 1. Probability should be normalized, right? If you do that, you can see this is followed, that nu over 1 over omega, and omega is a constant. We can bring it outside 1. How many microstates do you have consistent with that?
Omega.
Omega, so it becomes 1. So we use the normalization of probability. So it's a simple fact, but it comes from the normalization, assuming that it's 0 elsewhere. So this is a hand-waving argument. You can make it more rigorous by accounting that it's 1 for those omegas where the energy is in that shell. It's 0 otherwise. So far, today's class, this StatMech has had no connection with thermodynamics. It's as if you have just crossed the border from Italy and entered the German-speaking part of Switzerland, and suddenly you don't understand anything. So we have to make a connection. And that connection, your hint, lies in the fact that this omega is a function of NVE. In thermodynamics, we know that NVE are the natural variables to characterize entropy. Entropy is a function of NVE. So at this point, we make a bold claim and define entropy. You can think of it as the StatMech version of entropy, and we'll show in a bit that it is consistent with all the thermodynamic properties of entropy. We define entropy as omega natural log of omega as a function of NVE. And we also introduce a proportionality constant because we want to, and we call it KB. This is called Boltzmann's constant. So this is our definition of S is equal of entropy, that it is the log of omega NVE. Some people call it the Boltzmann formula. And on Boltzmann's grave, which is on the class website, and also the picture in the Slack channel, I think it is written as, let me go to the Slack channel and see. Is it on his grave? Is it S is equal to ln omega, or do they have S is equal to ln W? They have ln W. So you can see Boltzmann did not write the formula on his own grave. He was clearly dead by then. In fact, he didn't call this constant as Boltzmann constant. It came later. You have to be a really snooty scientist to come up with a theory and label the constant after yourself. You know, like this is my theory, and this is Sham's constant, or this is Smrithan's constant. You can do that. Maybe you will get away with it too. But let's see if this makes sense. Let's see how we can connect it to thermodynamics. So does this S make sense from thermo perspective? What are the things we should be looking for in order for it to make sense? Any ideas? What is the first thing we should look for it to specify the properties of an entropy?
Should be positive.
It should be positive. Is it positive? It's a natural log, right? So wonderful. It should be extensive. Entropy is an extensive quantity, which means that if you have a system made up of two different subsystems, A union B, and these are two independent systems, then S of A union B should be SA plus SB. Entropy is an extensive quantity. Is it followed here? Well, let's see. S of A union B will be given by KB ln number of ways of arranging system A, number of microstates the system A can have, multiplied by the number of microstates the system B can have. Why did we multiply inside log? Because A, B are independent, right? If they were not independent, the number of microstates for the joint system won't be a product of their individual number of microstates, right? It's independent system, that's why it's like this. This is a wonderful property of the logarithm, KB ln omega A plus KB ln omega B, that is SA plus SB. So it is extensive. And this probably gives you the answer to why is Boltzmann's formula with a log? Why is it not something else? This log is super important for extensivity. In fact, those of you who were interested in math Olympiads and stuff in your days of youth would recognize a functional equation which goes something like f of xy is equal to f of x plus f of y. You can show that log is the only function that follows this quantity, this functional relation. You can solve and show that it has to be a log. Apart from some trivial functions. So there is a, so, you know, after this class, someone comes and says, why did it have to be a log? Why did it could not be something else, which could also be positive, which could also be extensive, blah, blah, blah. It turns out no, because you have this, the extensivity. Currently, we proved it in the opposite way, right? We showed log means extensive, but you can actually show that extensive means log. There, it's a good point to mention, there are certain forms of entropy which are called Salis entropy, which are different from log. This is outside 687, nothing to do with 687. You can go and read up on it, where the entropy becomes non-extensive. Salis proposed it many, many decades ago. People still fight over it, whether it's useful in any way. People in Maryland seem to strongly believe that it's not useful, that it's so wrong for whatever reason, but it's non-extensive. If you want it to be extensive, it has to be log. Okay, what else do we expect? We also expect that the entropy, if you remember your 684, the entropy should be maximized in the absence of any constraints. If you add any constraints to the system, the entropy should become lower, right? This is something this is why entropy is maximized. If you go to Chandler's first chapter, Chandler's book is somewhere here, this is what he talks about. So is this really true? That's also easy to see. If you think of a system of NVE, let's think of a system NVE made up in two parts, N1 E1 E1 and N2 V2 E2. So this was a system together of NVE, and we put a constraint in the middle, and we say that the top part of the system has to have N1 number of particles, V1 number of particles, E1 number of, N1 number of particles, V1 volume and E1 energy, and the bottom part has to have N2, V2 and E2. So you can see clearly that the number of microstates for the system on the left is going to be more than the number of microstates for the system on the right with internal constraints. Why do I say that? Because any microstate on the right is clearly an allowed microstate on the left, correct? It's also sort of subtle argument. Why? Because any microstate here is allowed here, but not vice versa. So you can clearly see that the number of microstates is going to be maximized if you did not have any constraints. And log preserves this property. You could have had some other function which inverts this, right? Which log is monotonic increasing in its quantity that goes inside it. So since therefore log of omega NVE is more than equal to log of omega NVE internal constraint. And from this, our property of SNVE more than equal to SNVE with internal constraints follows. So it follows all the properties that we expect the thermodynamic entropy to have. And hence, it makes sense to call this S as our entropy. So that's our connection of the microcanonical ensemble with thermodynamics, that the microcanonical partition function, once you take its log, then it is going to be proportional to the entropy. KB is this proportionality constant. You might say once again, okay, it follows all the properties of entropy, but how do you know it is not just masquerading? How do you know it is not some sort of deep fake, which looks like it's the entropy, but maybe it's not the entropy? That boils down to this property that if, in order to be extensive, it has to be log. There is no other way. If this has to be true for all x comma y. Okay, so that's our entropy from microcanonical partition function. Now, this is really wonderful news because now that we have connected S thermoentropy to the log of the microcanonical partition function, now we know how to manipulate S to get all sorts of other thermostat functions, right? We have at our disposal the full machinery of thermodynamics of 684 or 481 or whatever class you have taken to get things out of it. For example, what is the first one we can think of? The first one we can think of is temperature. 1 by T is equal to partial S by partial E at constant number and volume. What does it mean? It means that 1 by T is equal to KB partial ln omega by partial E at constant number volume. Now, this is an interesting point to think what this implies about temperature and also get a bit of intuition into omega. So omega, remember what is omega? Omega, before you get lost, omega is the number of microstates with number n, volume V, and energy between just around E, just around the vicinity of E. And right now I told you that how tight is this shell around the vicinity of E won't matter. We will look at it later. But I want you to think about what would happen to omega as a function of E at fixed NV. Can we say anything about the number of microstates as to how will it change with respect to E? Any ideas and why? Can we say anything? Should it stay constant, decrease, increase?
This is very much a guess, but my
Mhm.
guess would be some sort of normal distribution centered at E.
Why do you make that guess?
It seems like it is most likely for the energy to be at E, but there is some non-zero chance for the energy to be away from E, an arbitrary amount.
So that's a very good chain of thought, Eric. The problem though is that it will come useful, not for now, it will come useful in canonical ensemble. What you are saying is your physical intuition that the system probably has a temperature, it has some average energy, right?
Yeah, I
And
think
maybe it can be colder, maybe it can be hotter, but it's got some temperature. But remember, this is an isolated system. We have no way of saying anything. So the number of microstates blows up with energy. And this is quite physical. If I tell you how many ways can you be in a ground state, is only one ground state, right? If you have taken in quantum mechanics, it should go to one at zero energy. The number of ways of being in equilibrium is typically very few, but the number of ways of getting distorted and getting to high energy states blows up. In canonical ensemble, we will be looking at omega. Canonical ensemble is when instead of NVE, we look at NVT, and we will do that in a few lectures. We will be looking at omega multiplied by something else, and then you will get the shape that you are talking about, okay? For now, no. For now, just the number of microstates. Whether we occupy these microstates or not, that's another story. Once you take that into account here, you will get this Gaussian picture. But for now, the number of microstates, the number of ways to arrange a system in high energy configurations increases as you increase the energy. So this is intuitive. You can be very rigorous about it. How do you be very rigorous about it? Well, you go and calculate omega. And when we do our integral to show that this choice of delta E does not matter, you will be doing something like that over here. But for now, you can see why this is intuitively true. when you take the system to high energy configurations, it's like I'm in my low energy configuration, I'm sitting. But now you want me to put me in a high energy configuration. I could be jumping, I could be doing this, so many different ways of going into high energy configuration. So that's why omega blows up. It's monotonically increasing at a very high rate. It's not just increases, it shoots up. And when we write, so in next class, we'll write down the exact formula for omega in phase space. And there you will see what is this dependence, how does it blow up when we show that the choice of delta E does not matter, okay? So what does this mean for temperature? This means that log of omega versus E is also going to be monotonically increasing. Maybe not so aggressively. You have muted it down. You have toned it down by looking at it on a log scale. This means, however, that partial ln omega by partial E is positive. It can never be zero, right? Because it's a monotonic increasing function. Or 1 by T is always positive, or temperature is always positive. So you could have gone in the other way around. You could have used that the temperature is always positive to show that this means that omega must always increase with energy. But we are taking a StatMech perspective. Number of microstates leads to this conclusion that temperature is more than zero.
Excuse me?
Uh-huh.
I can think of the relation between omega and E with the microcanonical example for, say, Ising model or something. But you mentioned that that curve has to blow up exponentially or very aggressively. Like, can you do it mathematically without any concrete model?
Yeah. When you say Ising model, this is something we will be doing in later parts of this semester. Keep in mind, anytime you have a model and you try to write down the partition function, you will be doing it for a finite number of particles in the system. All of what, anytime, and this is a good point to remind you that anytime we draw parallels between StatMech and thermo is in the limit n tends to infinity. Never ever forget it. If you're reaching some sort of contradiction, it's most likely because your n is finite. Thermodynamic limit means n tends to infinity, v tends to infinity, while n by v is finite. If you have any violation, most likely this is you are not in the infinite limit. You are not in the thermodynamic limit. Once you reach thermodynamic limit, all of these things will be true. Okay, and you will see example of omega in next class, not for an ideal gas, and then later you will also see Ising model, and you will be doing a lot with Ising model, so don't worry.
Yeah, so you're saying that even, say, without ideal gas or something, we can still prove some sort of concrete form or exponentially growing form of omega with respect to the energy, right? Or no?
I don't know if we can prove it without assuming a model. In that case, I would say that thermodynamics tells us that temperature is, I will go the back way. I will say that thermodynamics tells us that temperature is positive. This therefore implies that omega must be increasing with E. I can't think of a very general proof.
Okay, so it's just we can just say the monotonic increase for the omega rather than some sort of concrete form, right?
Yeah. We will be deriving a concrete form for ideal gas, but that's it. So yeah, and all of this again is valid in the thermodynamic limit. If you are willing to forego that limit of not having, in Ising model, for example, you can get temperature negative. And once you get negative, you will see that omega is no longer this monotonic increasing. And the reason why that happens, and you will be doing it in your second homework, is because you are kind of looking at finite number of particles in the system. But thermodynamics is thermodynamic limit per construction is n tends to infinity, v tends to infinity. Okay.
Yeah, that makes sense. Thanks.
Okay, good. So what else can we do? We just showed how we can get temperature out of this omega. We know that 1 by T is equal to partial ln omega by partial E multiplied by KB, or So at constant NV, or 1 by kBt is equal to partial ln omega by partial E at constant NV. So this 1 by kBt shows up a lot in thermodynamics. It has its own name. It is called as beta, or the inverse temperature. So you could specify the temperature T, or you could specify the inverse temperature beta. It's the same thing, just difference by a kb and on the reciprocal space. So beta is equal to partial ln omega by partial E at constant NV. So we got temperature out of omega. Great. What else can we get out of omega? How should we do that? We can use our integrated first and second law of thermodynamics, right? dE is equal to TdS minus PdV plus mu dN, right? Or TdS. So this is why I mentioned in the thermo refresher, never forget this equation, the integrated first and second law. In statistical mechanics, if you're getting stuck on a hard problem, you might go and frantically Google all internet forums to solve that problem and find a solution. I'm ready to bet you will probably succeed quicker if you just calm down instead of going over internet. Start with the integrated first and second law, and magically you will see everything falls into place. It's a wonderful equation. So, and why do we want to use it here? Because we just know that S is equal to K ln omega. So if you can write down ds in terms of other things, we should be able to manipulate it. So this means that TdS is equal to dE plus PdV minus mu dN, okay? Or ds is equal to 1 by T dE plus P by T dV minus mu by T dN. So what does this tell us? This tells us that 1 by temperature is equal to partial S by partial E at constant N comma V, which is something we already wrote down, but we get more things out of this. We also get that P by T is equal to partial S over partial V at constant N comma E, right? This one, by keeping this and this as constant. So how do we use that? So P by T is equal to this thing. So now we can say that P by kBT is equal to 1 by kB partial S. What is S? S is equal to kB ln omega, kB ln omega by partial V at constant NE. This kB cancels out. And we just introduced the symbol beta for 1 over kT. So P times beta is equal to partial ln omega by partial V at constant NE. So I think, who was asking me if there is a closed form expression for omega? Was it Jingchen or Z?
I'm Jing Chan.
Yeah, Jingchen was asking me earlier that are you going to derive a full expression for omega? You can see why he was so excited. I think the reason he was so excited, because if you could have such an expression for omega for any system, then you could get temperature out of it, you could get pressure out of it, and you could get the chemical potential out of it, because minus mu over T is equal to partial S by partial N at constant E comma V. And from this, you can see that mu over kT is equal to minus partial ln omega by partial N by V comma E. So at this point, I can create 500 homework problems. All you will have to do in them is to calculate omega for a given setup. Once you have calculated omega, you can go and calculate all sorts of thermodynamic properties, and you can go further. You can go from this and calculate many, many things. This is just the beginning. I showed you 3. So let me mark down the equations over here. So the first one I showed you is temperature. The second one I showed you is pressure. And the third one I showed you is chemical potential. And all of this followed from this integrated first and second law. So if you could get omega, you can calculate all of this. Now, calculating the microcanonical partition function is hard. There might be actually a computer science proof that it is NP hard. You cannot really do it. If you could do it, it would be very easy. You can do it for specific cases, and that's what we will be doing. And once we calculate omega for specific cases, we can get thermodynamics out of it. But not just that, we now also know the probability of a given microstate, which is 1 over omega, and we can keep doing wonderful things with it. So, and that's really the plan for this semester. Introduce 3 ensembles, write down their partition functions, connect them to thermodynamics, this first partition function connected to entropy, and use this connection to derive all kinds of nice things. That's the framework. You can create infinitely many problems on this basis, and some will be easy, some will be hard. You can derive things in chemistry, such as the Langmuir adsorption isotherm, simply on this basis. And so far we have done only microcanonical ensemble, so we don't really have all the tools. If you are a purist, you can do everything from here. But turns out constant number, volume, and energy are not often the best ways to control a system. Often you know something about the system, you couple it with a thermal bath, in which case you have constant number, volume, temperature. And that ensemble is going to be different from a constant number, volume, energy ensemble. And in which case we will have a canonical ensemble. So we will be doing canonical ensemble later, but this is where we are so far with microcanonical ensemble. Any questions? This is easy, but it's new material. If you have never done StatMech, this stuff is abstract. It's a different way of thinking. It's like the first time you do calculus. In retrospect, all of you hopefully think calculus is very easy, but you probably forget that the first time you saw the notion of dy by dx, it's one abstract concept. Like I was intrigued for 6 months as to why don't they just cancel these in the numerator and the denominator. And it took me a while to understand that you can't really do that. So this is abstract stuff. It's worth spending time on it and thinking about it carefully. Okay. So if no questions, let's think about this observation that I made, that the choice of delta E does not matter. Normally in this class, I stop around here because this is like first introduction to abstraction, but I'm gonna finish this today because Thursday I'm unfortunately unable to teach, so I don't want to slow down too much. So we defined omega NVE as number of microstates for n particle volume V system with energy in E minus delta E to E, this shell. And I made a claim, a bold claim, that the particular choice of delta E does not matter. So let's show that it actually does not matter. And this will be a useful exercise for 2 reasons. For the mathematical reason that we show that it does not matter, and also because you will actually calculate omega NVE. So it will give you some intuition into how to do it. This is not the only way to calculate NVE, omega NVE. For different systems, you can do different things. But for this one, this is how we are going to do it. So and again, you cannot calculate for any generic system. So we are going to do it. We are going to make an assumption. We are going to assume that these n particles are non-interacting. Okay, they don't talk to each other. It's a big assumption. But the funny thing about thermodynamics and statistical mechanics is that you can derive lots of interesting relations rigorously for non-interacting systems. And then you will be like, great, what do I do with this? Life is full of interactions. What's the point of all this? Then you can add interactions as perturbations to this model. You can say, okay, how about they talk to each other just a little bit? And then you will see you can go from your non-interacting theories easily to theories with interaction. Of course, at some point you will have strong interactions, and that's when things start to break down, but we will prepare a full framework. So this is actually a good point for me to show you how this course will really evolve. So we will do ensembles for a large time. We will apply these ensembles. And this is, if you look at the syllabus posted online, this is how it's presented there. We will apply these ensembles to the study of non-interacting systems. Then we will go to interacting systems. And then we will do further applications and examples, including phase transitions and things like that. So this is really the game plan for this whole semester. This is where all the theory lies. Everything else in principle is application, but it's not trivial. So it will look like it's a new theory, especially a lot of students tend to moan and loudly groan and make a lot of protests like, oh, this is so abstract. Why are we doing this? But this is actually the most important part once we get there. Okay, so that's just a picture for the remaining semester, but let's calculate this omega. To calculate omega, remind yourself that we are really thinking about particles in phase space. So you can think of it as R1. Yeah, let's use the symbol R1. So R1, R2, R3n, P1, P2, P3n, and it might, let's see what you get to here, something. Well, I was using X, so let's use X. I'll keep things similar, but it's the same thing. It's the position coordinate and the momentum coordinate. X1, X2 going to X3n. So every particle has XYZ coordinate. And I call the first particle's coordinate as x1, as instead of xyz, I call it x1, x2, x3. The second particle's coordinate, I call it as x4, x5, x6, so on and so forth. Okay, so these are all numbers. These are all scalars. We have 6n scalars. And what we would like to do is to look at the space made up of these scalars. So our R3n is made up of x1, x2, x3n, and our P3n is made up of P1, P2, P3n, right? And the number of microstates that are possible in this system are really the volume of this phase space. So what we want to do here is to calculate the volume in this very high dimensional space. It's going to be a 6n dimensional integral. 6n dimensional integral that goes and counts dx1, dx2, dx3n, dp1, dp2, dp3n. Why did I do this volume integral? The reason I did this volume integral, because if you were believing in quantum mechanics and you took into account that there are boxes that each system can occupy, then how would you have calculated the phase space volume? Then you would have done and said, let's go to every box and count the number of boxes, right? You would sum over boxes. But once you are looking at the thermodynamic limit where n is very, very large, it's okay to replace it with the integral. But if you're not doing quantum mechanics, if you're doing quantum mechanics, then this is not sufficient. We have to do some more stuff over here, which will come later. But for now, just think of a classical system. And all we are doing is to calculate the volume in this phase space. And that would give us the number of microstates, right? Because this is a microstate, this is a microstate, this is a microstate, this is a microstate, this is a microstate. And if we count all of them, that is the same as calculating the volume. But is this integral consistent with what I wrote up here? Or did I miss anything? Is this the answer, or do I have to consider something else?
So may I ask, how do you get the boundary condition since you have a constraint that omega, it must be have n numbers?
Precisely. That is exactly the point. With volume V, right? We haven't considered that. That's the one condition that we have to consider. And energy in E minus delta E to E, right? So it's not just an integral in full space. It has some sort of boundary, right? Because the X, you know, cannot go beyond a certain value. It's constrained in a certain volume. So how do we do this? In order to do this, let's separate out. So, and this is why calculating this microcanonical partition function is really hard. It's the complicated integral. But now remember, we have assumed non-interacting particles. So we can make our life easier. How do we make our life easier? Let's write down this integral as first integral over dx1, dx2, dx3n multiplied by integral over dp1, dp2, dp3n in the presence of all of these constraints with volume V and energy E minus delta E. And now let's focus on this configuration space part of the integral. These are non-interacting particles. So if you imagine a box of volume V, hopefully this looks like a box of volume V. And let's make a further assumption. Let's call it a cubic box of volume V, where every particle is free to go wherever it likes because it is non-interacting. The particles are blissfully unaware of everything else in the box. In that case, this part of the integral can be separated from the second part of the integral. Okay? There is no interaction between them. Furthermore, we can actually write down this part of the integral explicitly. How? Because if the box is of volume V, then each edge is of length V to the power 1 by 3, right? So each integral here is going to give us V to the power 1 by 3 multiplied by V to the power 1 by 3 multiplied by V to the power 1 by 3, and we have 3n such integrals. Okay, so let's number the equations so we don't get lost. So equation number 4 implies that omega is equal to V to the power 3n or V to the power n. It will be V to the power n, right? So 3n times. I don't mean you multiply all of them and then take to the power 3n. So you have each of these coming 3n times, and each particle, yeah, so it's V to the power n multiplied by the momentum part of the integral dp1, dp2, dp3n. And now we have taken care of the volume constraint. We still have to worry about the energy in E minus delta E. So, yeah, go ahead.
Could you go back to the previous slide? And so there's this is that a product of all the integral dx's with the integral dp? Is that because it looks like a hyphen, the red thing?
It's a dot.
Okay, cool. Yeah.
The product. And the reason we could do this separation is because the particles are non-interacting. If they were interacting,
okay,
they would be complicated. In fact, what we have tacitly assumed here is that the Hamiltonian of the system as a function of x and p is given by potential energy as a function of x and kinetic energy as a function of p. This is called a separable Hamiltonian, separable H, which has been split into a U plus K, where U is only a function of X and K is only a function of P. Almost all Hamiltonians are like this. If you start thinking about magnetic fields and things like that, life can get complicated. But most Hamiltonians, the ones that we are interested in, are going to be of this separable form. Furthermore, for non-interacting system, U of X is equal to 0 for non-interacting system. All that is left for a non-interacting system is the kinetic energy as a function of momentum, which is not equal to 0. That's what we need to calculate. So our omega now is in a relatively more tractable form, but we need to calculate this integral. How do we do this integral? We can actually write down the kinetic energy now. What is the kinetic energy? Kinetic energy is going to be P1 square by 2m. Let's assume all particles have the same mass, okay, just to simplify our life, plus P2 square by 2m dot 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 plus P3n square by 2m. And remember, I'm thinking only about scalars, so my life is simple. I have already done the component business. So this is equal to summation 1 over 2m, I is equal to 1 to 3n pi square, right? So this constraint can now be thought of as something geometric. What we are saying here is that we want to restrict equation 5. Equation 5 restricts momentum. And I'm going to stop here because next time I will start with this point. So you should think about this and we will restart from here. So I don't want to rush and finish it. I will stop here so you think and then we restart from here. So equation 5 restricts momentum to a shell in 3n dimensional space. And what is this shell defined by? You know that this energy 1 by 2m pi square must be less than equal to E, but it must be more than equal to E minus delta E, right? That's what we need to take into account. So if we were looking at a particle in 2 dimension, then this would correspond, if we had only P1 and P2, one particle in 2 dimension. So you can see there that this would be P1 square plus P2 square by 2m less than equal to E. What is that? That is exactly the equation of a circle. So you are saying it should be more than equal to E minus delta E, but less than equal to E. So all we care for is this thing in the middle. And here I have generalized it to 3n dimensional space. And next time I'm going to show you that this ratio of area by volume tends to 1 as dimensionality tends to infinity. And that's what we are going to use. You can read up on it on Wolfram Alpha or somewhere. It will give you some help with last class. This is only 5 minutes of math. It's not too bad. Then we will move to canonical ensemble next time. But you can read this up, weird properties of high dimensional spheres. High dimensional spheres sound as abstract things, but they turn out to be very useful for a variety of things. For example, designing, and this next part has nothing to do with 687, designing good anti-spam software is apparently deeply connected to packing of spheres in 7 and 8 dimensions. I don't know how, but it turns out that in 7 or 8 dimensions, you can pack spheres with a very, very high efficiency or something like that. And that means you can design very efficient anti-spam software. Or, I don't know. So high dimensional spheres are not just mathematical curiosities. They show up in physics quite a lot. For example, for a microcanonical ensemble, we will use this to show that the choice of delta E does not matter. So again, no class on Thursday, no office hour also, but I already see many of you are asking questions on Slack. So this Thursday, there is no office hour. I will have office hour the following Thursday, but keep asking questions on Slack, help each other out. And if you're having a discussion there, essentially your participation points are guaranteed. So please keep doing that. And yeah, any more questions?
I have a question with equation 5.
Mhm.
Should it be V3 or Vn?
Oh yeah, good job. Now I have to remember, I cannot make any mistakes about partition function with Neha. It's her favorite, so she would kill me. Yes, absolutely right.
Okay, thank you.
Good. Anything else? Yeah, so I just want to mention one more thing. When we cheat about quantum mechanics, we will be doing things like dividing it by n factorial and dividing it by Planck's constant to the power 3n. But this formula will show up in many different forms. I'm going to erase this cheating trick over here, but you will find later that if you just use this formula for omega, it actually leads to some paradoxes. And in order to solve those paradoxes, we will divide by n factorial. And that's our poor man's quantum mechanic trick. That we won't be doing any quantum mechanics for at least 6-7 weeks, but it's gonna happen later. Okay, so see you all later.
Oh wait, does omega have like units of volume to the n times like
What do you expect omega to have unit of? It's the number of microstate, right?
yeah, so
So
no
in principle, you expect it to have no unit, right? So this omega is going to have units of, that's where the paradoxes start to come in. It's good job. So if you stay with this omega, you will find that certain thermodynamic quantities are no longer extensive. They blow up with n. So that's why I said, if you divide it by h to the power 3n, then you can solve some of the problems, right? Because Planck constant has the unit of momentum multiplied by position. So if you divide it by h to the power 3n, you solve the dimensionality problem. Otherwise, this omega is not non-dimensional. It has some units, and that's a good spot. It will show up later.
okay.
Good. Anything else? All right, then. See you all on 9th February.